Hey everyone, it's MG from Computer Science 315. We're going to talk about hardware, so let's get to it. When we're talking about systems administration, likely you will be in charge of a lot of hardware. Sometimes, we're moving towards more cloud infrastructure or hybrid infrastructure. You might not have any interaction with hardware at all. Um, Even if you are in an organization or in a position where you have an on-premises infrastructure, it might, depending on how your team is separated from, say, a data center team versus a server engineering team, you may still have nothing to do with hardware. But it's likely at some point in your career you're going to have to deal with hardware. And there's certainly a lot of hardware out there for you to deal with. I personally, I really enjoy dealing with data center hardware. That's server hardware, storage hardware, things like that. I dealt with some networking hardware as well, significantly more when I was in the military than anywhere else in my career, but I still dealt with some networking hardware and monitoring hardware as well. So let's talk about a little bit of that. Um, we have servers, storage, networking, monitoring, and even security hardware. And this is just a general overview. We also have environmental and special case hardware, and we'll go into each of these sort of granularly over the presentation. So when we talk about servers, servers can be anything that serve up data or serve up a service. It could be a web server, it could be a database server, it could be a game server or an application or a web app server. And it doesn't need to necessarily be this big metal box sitting in a data center somewhere. It could be on a laptop, it could be on a smartwatch or a phone. A phone can be a server. But when we refer to servers in a data center or a rackable sense, we're thinking of the rectangular metal boxes that are measured in units, 1U, 2U, 3U. Each U is 1.75 inches, that are typically mounted in racks. We're going to see some examples of those shortly. When we refer to, or when we consider servers, we put them in racks, these big metal cages that sort of hold a bunch of servers. We have to consider cabling because cabling is important. Each server has, I think, minimum usually 7 or 8 cables connected to it at maximum. And, if you were to connect every one of them, to power usually, to network usually, to USB usually, a video usually. So there's a bunch of cables on the back of every server. And if you have populated an entire rack full of servers, you've got potentially 50 or more cables in the back. And we have to be mindful of power. We have to be mindful of airflow because airflow directly can impact temperature, which can directly impact performance and longevity and life of a server. So to combat that sort of that takedown in temperature and airflow and everything, they developed something called blade chassis. Blade chassis are still servers, but they're this big metal box that you put the servers into that consolidate a lot of the cabling and a lot of the cooling solutions, making it a super dense environment. So you're able to squeeze more servers into the same physical footprint by compromising on connections on the back of the server in a general sense. You may not be able to plug USB directly into a blade server, but you could plug it into the blade chassis and it will forward that USB connection to the server. Practically, there is no difference and it works just fine. We're going to see that in a little bit. So we see that this is a rack and we've got a bunch of little 1U servers kind of stuck in there with spacer blocks between them. We can see it looks like maybe this is a disk shelf right here. We're going to leave that for later. We can see this is a tape deck with another 2U server and another 2U server, and looks like an iron port, if I'm not mistaken, which is a security appliance. Right here, we can see we have an HP Moonshot, which is an ARM-based blade chassis that slides out, and we insert blade blade slices. I think that's what it's called, Moonshot slices vertically, and these are ARM-based individual computers. So all these little slices are individual machines, and I think these bigger ones might be disk or storage. Here's a super micro blade chassis where I think we have 20 servers, 5 in each little bay. In the space of what looks like 1, 2, 3, 4, 5, 6, 6U. maybe 7U. So significantly more in the same footprint than if we were to just put 20 servers in a rack. We can see this is a standard 1U server from Supermicro. It's got a bunch of disks in it, but it's just a standard server taking up 1U. This is a 2U server that's actually comprised of what looks to be at least four. It might be these might be individual bays, so this might be 1 and 2, 3, 4, 5. There might be 8, but it's at least four of these nodes of these blade servers. So this is really good. We want to densify this way. When we talk about storage, there are a few offerings that come to mind. Disk drawers are the oldest and sort of most, basic of storage hardware out there. They're effectively a drawer of disks, of hard drives, that are directly connected to a server or potentially two servers. Usually these are single server. For the sake of the exam, these are single server connectivity type situations, usually with more than one link in case one goes down. And whenever you're whenever you're using these in the operating system, it looks as if it's just a giant hard drive or a series of hard drives that's attached to the operating system. It doesn't really have, it may have a controller card or a connection card, but usually these don't have a lot of intelligence as far as managing the storage is concerned. And these are good whenever you just need to add a bunch of storage to a single server. But these kind of fall by the wayside in favor of NAS and SAN technology. Speaking of which, NAS, network attached storage, is storage that is connected to the network using typically gigabit Ethernet. And if we were to take a step back, even enterprise grade NAS solutions are effectively a computer with a bunch of directly attached storage that's sharing that storage over the network. Usually it's file-based storage, which is a protocol like NFS or SMB or AFP, but in some cases you could share it out via a block level protocol like iSCSI if you wanted to boot to it. Again, this typically uses gigabit, though I guess it could use 10 gigabit networks, Ethernet if you wanted to. However, for really lean, precise, performant computing, storage area networks are really where we're at. That's the most enterprise solution that we can manage. That's still network connected storage, but it uses a separate storage network that's delivered typically using fiber channel connections, which are significantly more faster and performant than gigabit Ethernet, just by the way that they work. It uses light instead of electrical pulses, and it's usually 40 gigabit or 80 gigabit, and you could put a lot more through it. Also, storage area networks have a controller component that allow a lot more configuration and management of the storage that it's in control over. You could slice and dice it up a little bit better. You can group them together a little bit better. You can still do some of this in the network attached storage, but usually that's being done on the operating system level of the NAS, and then you share it out a share at a time. SAN, it delivers block level storage to an operating system or to a server that's been pre-cut, pre-made redundant. It's really the best way to go about things. We could see right here we have a few SANs, and this thing was at the time that I took this picture, this was the most recent SAN. But we can see we have some SANs down here. We have a SAN right here. We have another SAN right there. And if you look really closely, you could see that we've got a blade chassis right down there. The middle image is of a backblaze. Southeastern purchased a backblaze to try it out. This is a NAS, and you could tell because it's got its motherboard back here, a bunch of power supplies to power all these disks, and then 3 expansion cards to handle each set of multiplexers right there. These are just SATA multipliers. So I think this is 42 drives or 42 drives maybe. And this just shares it out as an NFS or an SMB protocol. And then we have a single U storage server. This is just a bunch of disks in a server. That could be a NAS, and this is also a NAS. We don't have any directly attached storage. In fact, this actually may be direct attached, but technically it's a SAN, but I think we were using it as direct attached. And this is just a NAS as well. Moving on to networking hardware. When we talk about networking, we typically think of switches and routers. A switch is a dumb router. It passes network packets to and from devices on the same network. And a router is sort of like a smarter switch. It does everything a switch does, but it also passes network packets to and from devices on other networks as well. So routers connect to each other and switches connect to routers. A lot of functions of switches, or a lot of functions of a switch are implemented in routers, but there's the distinction of being able to cross over that network barrier. These can be rack mounted or wall mounted. Rack mounted, it's really simple. It's just shoved into a rack. It's a single U typically, but it can be more. In fact, there's actually blade technology with networking gear as well. If it's wall mounted, it's typically mounted vertically on a wall, kind of hanging off some brackets, flat up against the wall, and all of the networking sort of plugs into it vertically. This is a centralized, decentralized mentality in that, whenever you want more ports or more network in a certain place, you put a switch and you run, whether it's a gigabit line or 10 gigabit line from that switch to a different switch, and you sort of just keep expanding your network that way. And it's centralized in that you have a lot of devices connecting to that switch. So you sort of localize to a switch and then you decentralize to other switches. In this case, building one switch has 3 devices. These can represent n number of devices. It doesn't have to be exactly 3. Building 2 also and the core switch have 3 as well. We call it the core because it's the main router's switch. These could be physically separate devices. These could be an all-in-one device. It doesn't really matter for the sake of the diagram. The nice thing is we are able to have amounts of resiliency built into networking by making redundant routes. So building 1 connects to the core switch, that connects to the building 2 switch, which also connects to the building 1 switch. If we were to sever a line between a connection between building 1 and building 2, we could still connect to the devices in building 2 from building 1 because we are going through the core switch. And if we sever any other link on there, as long as we have a route to it, we're able to connect to it, which is really nice. This is fundamentally how the internet works, except it maybe does it through switches and routers, a lot more switches and routers than just these 3. Another thing that networking has in it, and sometimes it's a hardware appliance, but a lot of times it's built into other hardware appliances, is something called quality of service, or QoS. QoS gives us the ability to prioritize traffic based on the type of traffic it is, and that could be based on a port, that could be based on some packet inspection, where we open up the packet and look at it and say, hey, what's your goal? What are you doing? Are you video? Are you voice? What are you doing? This is a good way of prioritizing certain parts of your network. For instance, we could make Moodle run extra fast, or Moodle have top priority, or Leonet or Workday have extra priority, but things like YouTube maybe takes a back seat. And QoS typically is only ever implemented when you've maximized your connection. So it's not like it's going to slow down YouTube at late at night when no one's on it. But if you ever hit 100% peak usage, QoS might jump in and do its thing. That's not that those are all for examples. We don't actually do QoS at campus, as far as I know. Here are some examples where we have a networking rack specialized for networking gear, because it's got this sort of beveled in chamfered edge on the side where you've got a lot of cable management on the sides, which is really helpful. Everything's able to kind of go through these little wire wraps and connect up to these. These are actually switches, look like standard gigabit 48 port switches with fiber uplinks. That's what the orange is right here, the orange cables. And then we get a bunch of I can't remember the name for them, but these are effectively connected to another switch or connected to a place in the building. Patch panels, that's what they're called. So we have a bunch of patch panels that just make it easier to configure and easier to connect up. In the middle, we have a blade chassis for networking gear, a switch blade chassis, and each of these sort of rows right here serve a different purpose. We have some blanks, looks like in the third or the fourth, fifth, and the eighth slots, but this slot and this slot are controller boards. I know that. This looks like an SFP board that doesn't have anything in it. These are SFP boards with gigabit or 10 gigabit copper connections in there, and then this looks like another maybe extra fast SFP fiber board. And then we have specialized racks. They don't have to be all big like server racks are. We could have specialized racks which are a little bit smaller, um, and do the same job of organizing and holding switchgear. Switchgear is usually pretty light unless it's a chassis like this. The chassis are pretty hefty things. We can have monitoring hardware. These are devices that look at the traffic and activity in your data center, and they model trends and mine data over time for a few reasons, right? We could look at our security baseline or system performance over time. We could manage uptime, decide, if something goes out, we have a service outage, we could determine maybe what happened. In a previous presentation, I mentioned logging, and one of these monitoring applications, one of these monitoring pieces of hardware could conceivably do logging. So this could be a Elasticsearch running on whether it's a CheckMK rail like this or anything that would run a monitoring suite. You could run a bunch of captures on it. For security hardware, we typically have three big ones: IDS, IPS, and firewall. IDS stands for Intrusion Detection System, and this is a system that sits in your network and looks at all the traffic that's coming through and detects attacks. And when it detects an attack, it alerts a sysadmin. This could be an internal attack, this could be an external attack, but it says, "Hey, this is flagged. I'm gonna tell you about it. Maybe you should do something." And then we have IPS, which is Intrusion Prevention System. It does the exact same thing except it attempts to block the attacks. Now, the question you might ask yourself is, why would we not try to block the attacks all the time? And the simple answer there is, one, good IPS is hard to find sometimes, or if it's not hard to find, it's expensive. Uh, a lot of free or open source IPS offerings are community based, and there's sort of this subscription to a pattern file or a naughty list of types of attacks. And either it's not that good, or there's some reason the organization that you might be working in won't be able to use it. So good IPS is hard to find, but if you can pay for one, I recommend that you do. If you can fully define define your habits and define the types of traffic that's going to come in and out of your network, then an IPS might be good for you because you know exactly what's going on. With a big organization like a university, where there's a lot of different types of users, there's a lot of different types of traffic flying around all the time. You don't want to put an IPS out there because when it detects something, it might get it wrong. It might not actually be some bad traffic. And instead of just alerting you and saying, "Hey, this happened. Do you want to look at it?" and you going, "Check, that's fine, acknowledged," it actually does something, and it maybe blocks that user from doing something. So again, in the realm of security, blocking someone from doing something, even someone that has no intent of doing something bad and inconveniencing the user, that's acceptable compared to losing all your data, exposing all your data. But a lot of the times it isn't this or that, this compared to that. More common though, we have firewalls. Firewalls are, on your laptop or whether you have a Windows or a Mac, you have a firewall installed on your system. It's a software-based firewall. And software-based firewalls and hardware-based firewalls effectively are the same, except one lives on a dedicated machine, and software firewalls are integrated into your operating system. And it's based around a rules-based mentality. So a hardware firewall, is a rules-based appliance. And based off of a series of rules, it either permits or restricts certain types of networking traffic in and out of your network. And you could have firewalls at several places throughout your network. You could position them, at the router level. Whenever one network is changed into another network, you can put it at the edge where, it goes from your intranet to your internet. Internet being the big world, and intranet being the small series of networks that you can control. Firewalls are really important, and they take a diligent eye, but they're very, very important. We can see that security appliances look no different than just a bunch of colored and logo rectangles. We have colored, logo rectangle here. This is a pfSense box. We've got looks like this is from, I can't remember what this is from, but it's got a little bit of a networking bit in the front, little switch in the front. And then we've got Fortinet's big giant thing where we've got sort of like chassis, again, blade chassis for networking gear. which is pretty cool. So you could plug all your networking gear in here, and it will do security as well. Talking about environmental hardware, this is a little bit less of what a sysadmin might be in charge of configuring, but it might be something that you, as someone who lives in the data center, has to contend with. You have to be aware of it. You have to know how to deal with it. You have to be able to look at it and manage it, and and at least be aware of it. So the first thing up is a UPS, an uninterruptible power supply. This is a giant battery backup. Think about what you've plugged your desktop or your laptop in, that APC or Triplite or Cyber Power box that has a battery in it. Keep it up, keep your laptop up for 40 minutes, 50 minutes in a power outage. They are almost necessary and valuable in southern Louisiana with all of the storms that we have and the power outages we have. Imagine the same thing, but significantly larger and delivering way, way, way more power. It's meant to keep devices powered on temporarily during a power outage. They are not a long-term solution because they are just a big case of batteries. Batteries, especially for the amount of equipment we're talking about in a data center, batteries don't cut it for very long. You'd be lucky to get 20 minutes out of a series, and I'm talking three, UPSs in a data center. In Southeastern's data center, we have two generators outside, and the generators are the only point of the UPS is to keep the data center alive, so that the UPSs can start, or the generators can start up. They can reach maximum spinning speed. They can begin generating enough power consistently, and then we can switch back over so we can get power from the generators instead of power from the power grid. The only purpose of the UPS is that temporary sort of float between losing power, grid power, and getting generator power. It's really important to understand that UPSs are not permanent solutions. Air conditioning and humidity controls, these are incredibly important in a data center because if you don't maintain appropriate temperature and moisture levels, you're going to have a bad day. It doesn't like to be computers don't like to be too hot. They don't like to be too cold. They don't like to be too dry. They don't like to be too wet. So I think we kept our data center at about 72 degrees Fahrenheit. And if you lose air conditioning and you still keep everything online, you will know it very, very quickly, because all of a sudden it will rise several degrees every minute, and it's a big deal. Too dry, it's a fire hazard. Too wet, it's an electrical short hazard. So we need to maintain things appropriately, and this is going to vary based on your climate. So you're going to need to do a little research about that. This is what they look like. This is a series of right here. These are big giant UPSs, and there's a big power bar at the top delivering power, and these are individual racks that are just powered from these UPSs. So this is a UPS, that's a UPS, that's a UPS. This may be a UPS as well, just a larger UPS. I'm unfamiliar with that. And then we have these are some Liebert air conditioners, and they are the size of an entire rack of servers. This one's actually the size of one, two, and about 3.5 racks of servers. What they do is they suck air from the top and they blow air straight down. And these really work on an elevated sort of surface. The data centers that I've been in typically are elevated about 18 inches off the ground with a raised floor. There are certain floor tiles that have perforations, a lot of holes in them, and because of the pressure of all of the air going straight down, it pushes the air up through the perforated tiles, and those perforated tiles are just organized right in front of the racks of servers. So the cold air shoots up and then is sucked through the server. The hot air is blown out the back of the server rack, which is then collected at the top of the air conditioner and recycled, and it's the cycle. It's the circle of life. We refer to special hardware, and these are sort of catch-alls, but they're important. If you're getting away from legacy PBXs and telephony hardware for telephones, you might be going to voice over IP, which uses the same IP-based network that everything else uses in your environment to deal with phone calls. This is a VoIP server or a VoIP appliance would be something that would broker telephone calls using those IP networks. Load balancers are devices that take in requests from users or from systems, and it divides that request amongst a series of machines of servers in a pool. So it distributes the load. We have this for Moodle, we have this for LeoNet, we have this for a series of things. Whenever you look at whenever you go to a Facebook, whenever you go to Google, whenever you go to Yahoo or Twitter, you're not all going to the same machine. You're going to a load balancer that is distributing your load across the entire world to many, many, many machines out there. So it's very unlikely that you're going to be on the same server as somebody else. The great thing about that is whenever you're doing maintenance, you can just take the machine out of the load balancer pool and take the machine down and do whatever you need. And whenever you're done, put it back in the load balancer pool. The downside about that is you do have to have several machines that are effectively serving up the same data. So you're paying, you're over provisioning for that balancing ability. We have proxies, which kind of do two things. I didn't put the second thing on here yet, but proxies typically are appliances that forward requests from one server to another. So we think about VPNs. VPNs are effectively proxies because we are acting as if we are some other machine. But proxies also can do something else, which is kind of cool, where if you set it up the right way, proxies can hold external data locally so that it speeds up access of that external data. For instance, common data that you might not realize is just always there. Any mainstream like site out there is going to have a logo. That logo probably doesn't change very, very often. So if you held that logo in a proxy and you passed through that proxy, and whenever you needed to go to that website, instead of loading the logo from the website itself, you loaded it from your local proxy, it would probably be faster. Now, extrapolate that for everything that doesn't change very often. Clearly, news articles, they change every day or whatever, so you'd want to go out and get those fresh because you need the up-to-date information. But if all of the images on a site or all of the common images on a site were never changing or changing very infrequently, you could store all that locally. And let's just say you have a limited bandwidth situation, you download that information once to the proxy, and then everyone locally just accesses that proxy. Let's just say it's in one building or something, one site, one geographical site. Everyone would access that proxy and load that common data from that proxy. So that could be a way to save bandwidth and save money as a result. And then we have streamers, which are appliances that can encode raw video and audio and create a network stream to pass through the internet or through an IP-based network. This is typically something that has, specialized hardware that takes in either raw video or some type of medium that converts it into a network. Most of this hardware resides in data centers, and the great thing about data centers is that they are centralized in that they have environmental control set up. It's already set up for management. That management can be, we've got security cameras, we got people. There are closets and tools if we need to work on something. If we need a cable, there's chances are it's all that. There's power and there's networking and there's already this control that exists there. But you can decentralize a little bit and go to networking or wire closets. You could put things there. The downside is you're going to have a power and an environmental solution, whether that's HVAC, moisture control, or whatever, in those networking and wire closets. Usually, if it's one or two things, maybe you can get away with like an APC battery backup. That maybe you're okay with that wire closet going down whenever there's a storm and you overrun your battery backup. And then finally, fully decentralized, you've got the cloud-based data centers, which, whether this is AWS, Google, or whatever, you're able to push all of your workload to the cloud or hybrid workload to the cloud. You're able to get it out off of your on-premises hardware, and as a result, you sort of transfer the risk and the responsibility of uptime to whatever company you're paying. And again, that's money, but you pay for what you get, and sometimes, or you get what you pay for, and sometimes it's really worth it. So to sum up, there will always be hardware. It's not like when you go to the cloud, there's no more hardware. It's just someone else's It's someone else's computer. It's in someone else's data center. And they're probably better at it than you are because you're paying them. They're not paying you. Most hardware appliances are a server architecture level system, usually some form of customized Linux operating system at the lower level. It's packaged with specialty hardware if necessary. So for those security appliances that had, maybe some gigabit or 10 gigabit network ports on the front, that's just a specialty hardware package that's plugging into a motherboard that can accept it. And they're usually branded. They have logos, they have paint schemes. They're practically race cars. But understand that if you can buy it, chances are you can DIY it. You can build it yourself. But there's some pros and some cons to that. If you're building it yourself, the pro is going to be the big one. Cost is going to be significantly lower if you know what you're doing. You're going to have all the configuration options that you really desire. You'll be able to make this thing very specific, do everything you need it to do, and you'll learn why doing it. That's such an important thing. People don't really value, I guess, as much as I think they should. The downside is uh, there is a lack of maintenance because you built it. There was a lack of support because you configured it. You're the one with all the knowledge that you gained. And while you're building this thing, you have to ensure that there's some compatibility with your ecosystem. And that might be really hard depending on your environment. Now, on the flip side, pretty much everything, if you buy it, there's a dedicated support team. You pay them to tell you why it's broken and to fix it. Sometimes the support team's not that great, but you do have one. It's paid for compatibility. If unless they lied, you gave them money, they gave you a product that has been tested and ensures that it's supposed to work in this environment doing this thing. However, it might be very expensive, and that sometimes is an initial expense and a recurring expense for maintenance or for support. There may be a lack of configuration, or on the opposite side of things, it may be so overkill. It might be you use 20% of it and 80% is never used by you, but you can't get just the 20% with the buy option. When we look at some of the things that you can buy out there, this is just a firewall, an 8-port gigabit firewall, $15,000 almost on eBay. Um, or I'm sorry, $50,000 from NeoBits, $8,000 from eBay if you wanted to get it, used. Uh, this Barracuda web filter, it's a security appliance with 5 years of updates, 200 and almost $60,000, and you have to pay shipping. I mean, that's pretty ridiculous, right? But I mean, there's a lot to be said about doing something like this. So these things are pretty expensive. DIY might be the way to go, especially if you're just proving a point. Um, when we look at data centers, we could tell this is a really nice data center. It's raised floor. These tiles are raised. You can't see it because it's probably water cooled, to be honest. But you can tell by the way that these posts go into the floor that it's a raised floor, and it just looks really nice. Minimal lighting, probably decent temperature in there, just really great. These lights probably change based on any type of informational status or whatever. So it's probably good, or it'll be green or red. It'll be bad. This looks like the hot aisle, so this is probably orange for a reason. And these are open air servers, so there's no conventional. These aren't Dells or IBMs or whatever. These are open air. They're probably built custom on a tray that just doesn't have any. It doesn't have any airflow blocking at all. Probably because they're water cooled or something like it. Um, and these are another version of that. You can see that they're kind of open. These are Google data centers, so it makes sense. These slide out. It looks like maybe 2 or 4 on a tray. There's some heat sinks, and the heat just goes up and probably gets either sucked in the back or there's a blower somewhere. These might be blowers up there. You can see there's some cable trays. There's a big giant power bus bar with these big giant circuit breakers with the red little circuit breaker right there. We can see this is a Google engineer. She's pulled one out, and it looks like these are direct DC power, right? So your power supply in your typical computer converts AC to DC for use in the computer. The fact that this is a red and black cable lead me to believe that they just plug into sort of a power bar built into the rack. They could do that because it's Google. It's pretty good. And then we got like more what you're probably going to see in your life. It's not going to be great. We've got the perforated tiles down here, shoots the air up, because we need to cool this mess. This is all networking stuff. This isn't even racked. This is just kind of sat on top of whatever server this is, and it looks like we had some good networking probably by a contractor at some point with this purple cable coming up, but yeah, all this garbage back here just didn't work out for us. This is more of the same. It's a lot of patchwork. We're trying to patchwork. I think this is probably a joke. This is probably storage or an old mall or an old data center that's just no longer in use. So we can't really can't bite on that one too much. Um, this guy, I think this was a video still of a before. He was going to disconnect everything and reconnect everything. You could see him kind of working right there. Just all of the spaghetti is terrifying. But it's nothing compared to this one. This is my favorite because this is just cheese, right? This is just horrible. I don't understand how anyone could have done that to themselves. And then finally, this is what happens. You connect a cable. You don't custom length your cables. You don't cut them to length, and you have I have a 16 foot or a 20 foot or a 50-foot cable, and you need to connect from right here to right here. So you go, I'm going to connect it. I'm going to spool it up on the ground a million times, and then I'm going to connect it right there. And all you needed was a 4-foot cable. So total mess, but it is what it is. But that's how hardware works. That's a general overview of hardware. This is going to be the material for the very first exam, so please rewatch this. Send me an email if you have any questions, mg@selu.edu or mg@southeastern.edu. If you have any questions at all, I'd be happy to answer them either via announcements or Q&A or something like that. So until the next video, everyone, thank you so much. Have a great day.